So in this example, we're given a system of three parallel forces. All right, FA, FB, and FC, and they're all applied to the pedestal that's shown here. And we're asked to determine where could we apply a resultant force. So our goal is to find the total resultant force. All right, and where on the pedestal is our resultant force being applied. Okay, so first thing we need to, in order to do that, is we need to find. So we can, first thing we can do is we can find our resultant force. That shouldn't be too hard. Our resultant force is just the sum of all the forces applied to our system. So in this case, it would just be equal to FA plus FB plus FC. Okay, so let's just do that real quick. All of these FA, FB, and FC are all along the z-axis. So their x and y components will be, we can ignore them. All right. So based off of the problem description, FA is equal to minus 300 pounds. FB is equal to minus 500 pounds. And FC is equal to a positive 100 pounds. So if we add these all together, our resultant force would be equal to minus 800 plus 100, which is just minus 700 pounds. All right. Then the second, so we have our resultant force. All right. So the next thing we need to do is we can calculate the moment caused by all of our forces about our origin point. Okay, so we can find our resultant moment about the origin, which would be equal to the sum of all of our moments plus so the moments due to our forces plus any couple moments applied to our system. In this case, we have no couple moments applied to our system, so it'll simple down to just the sum of all of our moments at point O. So this would be equal to the moment due to force A, which would be equal to R of A cross F A. Then we would get R of B cross FB for our second moment, and then R of C cross FC for our third moment. So we can evaluate each of these cross products individually, and then we'll sum them up to determine our resultant moment. So let's start with RA cross FA. So R of A is going to be equal to 4 inches along the x-axis, so it would be equal to 4 inches times I. Alright, and then this would be cross F of A, which was given to us as minus 300 pounds times K. Alright, so if we multiply that across, we can multiply our two scalar numbers together, so we get 4 inches times minus 300 pounds. Alright, and then we would get I cross K, alright, for our cross product. So if we remember our cross product circle that we described a few lectures ago, all of the cross products, so I cross K, J cross K, K cross I, these are all counterclockwise cross products, which means that they would create a positive moment, while if you multiply if you go clockwise around this circle, So like I cross J, I cross K would be negative. K cross J would be negative. J cross I would be negative. All right, and that's it. So what we end up getting here is we get minus 1200 pound inches times a I cross K. We would get a negative J hat. So what we end up getting is 1200 pound inches times the unit vector J. So we can move on to the second cross product, which would be RB cross FB. All right, so R of B was defined as 4 inches minus 4 inches I plus 2 inches J cross a minus 500 pound force going along the Z axis. So if we multiply this across, we get 2,000 pound inches times I cross J, or I cross K, plus minus 1,000 pound inches I J cross K. So from this, if we go back to our cross product circle, I cross K is going to give us a negative J. So what we'll end up with is minus 2,000 pound inches times J. And then we'll get a positive, we'll get a minus 1,000 pound inches times J cross K is going to give us a positive I. Okay. All right. And then the last cross product we need to determine is RC cross FC. And if we do that, we get RC is equal to minus 4 inches along the y-axis, and F of C is equal to positive 100 pounds along the z-axis. So we take that cross product, we get minus 400 pound inches times J cross K. All right, J cross K should give us a positive I based off of the cross product circle. So we would get a minus 400 pounds I. Right. So if we add these all together, what we end up getting is our resultant moment. All right, so we add all of our x components together. What we end up getting is we get a minus 1,400 pound inches in x, and we would get a minus 800 pound inches in y. And then we can find so once we have okay, so now we have our resultant moment about our origin point. And I should have drawn it along the xy axis. So it's along 1,400 and minus 800. So that should be going along this direction somewhere. All right. So what we need to do is calculate the position vector from our origin point to our resultant force that would create that moment about our origin point. So to do that, we know that our resultant moment is going to be equal to R cross our resultant force. So we can write, we know our resultant moment as a Cartesian vector, so we could push that down here, and we know that the cross product is going to be equal to I, J, K, and then the second row would be equal to the components of R, so it'd be equal to Rx, Ry, and then 0, and then because it's going to be sitting on the pedestal, the Z component would be equal to 0, and then our resultant force we know is equal to 0, 0, and then minus 700 pounds. Alright, so we can copy our next two rows, or the first two columns of this matrix. Alright, and we can evaluate this determinant. So if we do that, we end up getting just we get minus 700 pounds R of Y times I, and then we're going to get, for all of our negative diagonals, we're going to get a couple zeros, but we'll get minus 700 pounds Rx times J. So what we end up getting is we get minus 1,400 pound inches times I plus minus 800 pound inches J is going to be equal to R of Y is going to be equal to minus 700 pounds times R of Y I plus 700 pounds times R of X J. So we can set our X components and our Y components equal to each other. So if we set all of our X components equal to each other, what we would get is we get minus 1,400 pound inches would be equal to minus 700 pounds times R of Y. R of Y would be equal to 2 inches. Alright. And then if we did the same thing with the Y component of our resultant moments, we would get minus 800 pound inches would be equal to 700 pounds R of X. R of X would be equal to minus 1.14 inches. Okay. So if we go back to our original diagram here, we would have this point of application, or of R, would be at 2 inches along the y-axis and a 1.14 inches along the negative x-axis. Okay, so that's where our equivalent resultant force would be applied. That would create the same equivalent moment of our system about the origin of our system. All right, so these problems are pretty straightforward. You have to just find first you find the resultant forces and the resultant moments using some of all your forces, Cartesian forces, and some of all your moments using cross products. And once you have those, then you can set to find the location of where your resultant force would be applied, you would take the cross product between those two vectors, and you would substitute in values for r of x and r of for your unknown coordinates, and you can solve for those unknown coordinates using the sum of all the moments in the x direction and sum of all the moments in the y direction.